I shut down the website last night. I was receiving, I noticed it too late, but I was receiving a lot of spam email signups, and it was sort of distracting from genuine signups. And it wasn't to my main page, which actually does have captcha included, but it was to my request access page for the Genealogy project. And although it's a login form, I realized that since it also acts as the sign up part of the website, it doesn't make sense for it not to have captcha, because it just allows this sort of activity to occur. So this morning I have to go through and add in captcha again, introduce Google Analytics to the other pages as well, just so that I can notice this activity. Other than that, the website seemed okay. I just have to be, it was a good lesson to learn anyway.
So it's actually a few days later now. I did actually end up fixing the captcha issue on the same day. I'm actually glad that it broke, because I realized that the response from Google wasn't being verified correctly, and now it's all sorted. So as a result, I've managed to eliminate all spam activity, so that's all good. Now, while fixing that, I realized that I had made another mistake with the Genealogy project, particularly in the way we were generating the graphs for it. So as a recap, I take my first node and I place it in the graph. And then in order to add another node into my graph, I need to have a direct link between the node that I have placed and the node that I'm trying to insert. So as an example for how this process works, if we have three nodes, a mother, child, and grandparent, and we start with the child node, so we place the child node into the graph because it's the first node, it gets placed. Then if we get a grandparent and we try to insert it into the graph, that grandparent is not going to be inserted into the graph because there is no direct link between the grandparent and the child. So we have to skip the grandparent for the moment. Then the next node that we get is the mother. Now there is a link between our mother and our child node that is already in the graph. So that direct link allows us to place it into the graph. And now since the mother is there is a mount point for the grandparent. So when we get the grandparent node, we can then place it. So this is the fundamental rule of how the graphing process works. You need a relation in order to mount a node or insert a node into the graph. The next thing to understand is, for my first solution, every single node has an up, down, right, and a left. And you can think of it as all nodes above are going to be parents, all nodes below are going to be children, all nodes to the right or left are going to be partners. And so this is how I connect the nodes to each other. So as I was saying, I was having issues with this process. And if you look at a concrete example, so we have a graph here where the yellow nodes are the nodes on the top, the green is the node in the middle, and then the orange nodes are at the bottom. When we map this graph out, it should end up looking like this. with B, C, and E having a transition between them. However, that wasn't happening. Instead, each of these nodes, so B, C, and E, assume that that transition node actually belonged to them, and they weren't actually seeing the nodes beyond that. So this was a big issue. They weren't correctly connecting to each other. The fix is actually not that simple if we aren't recording the positions of these nodes relative to each other. So if you're only connecting them up in this graph way, so with the up, down, right, and left, and we aren't recording their positions, so a coordinate for them, then we aren't going to know what nodes are next to each other or where they are. One strategy that I explored was to try to create a buffer zone of transition nodes surrounding each of our inserted nodes. So, for instance, to begin with, when we insert A, we surround it with a set of transition nodes that are already connected to each other. Then when we insert B, we can insert it into one of these existing transitionary spaces, and then start expanding B from there to create its own buffer zone. So this involves checking a 3x3 grid centering around the transit node we are trying to insert to make sure that we can connect to any nodes out there. So starting with the top right, we scan a 3x3 grid centering around that top right node to check which nodes are actually available to connect to. Likewise, for the bottom right and right node, we do the same thing. So this process is still error prone, particularly if we aren't using a reference grid to work out where our nodes are placed. And if we are using a reference grid, then it's easier to just go with a nested dictionary approach, which is what I ultimately ended up going with. With a nested dictionary approach, we can assume that the first dictionary contains each of the columns in our graph. And for each of those columns, there is another dictionary within them that contains each of the rows. So if you go back to our original example, so as a reminder, the yellow nodes are at the top, the green is in the middle, and the orange nodes are at the bottom. So if we take these nodes and we start off with C and we want to graph them out using a nested dictionary approach, so we would insert C at location 0, 0. Then every other node that we place gets placed relative to the first node that we have placed. So using the same fundamental strategy that we had before, we're going to place each of our nodes only if they are directly connected to a node that is already in the graph. So when we get D, D gets placed below with key 0, 1, A at 0, 0, negative 1, E at 1, 1, and B at 1, negative 1. Now, if we want to find out the actual location of B for the purposes of rendering this out using Conva, for instance, then we don't want to be working with these elements in that negative space. What we have to do is translate them into a positive space. The easiest way to do this is to identify the lowest x and lowest y value. Now, for us, in this particular example, both those values belong to node A. So the translation is going to be by 0, negative 1. So we want to translate this graph by A such that A becomes 0, 0, and everything gets laid out relative to it. Now, once all of the nodes have been translated by the lowest x and lowest y value, you will find that they will have a positive x and y coordinate as well, yet they will be placed relative to each other. So nothing has moved as such in terms of the relative space. So that's about it. That's all I wanted to share. Thank you and goodbye.